So what are the topics to know for our diffie-q with linear exam 3? The point here is to do a broad overview of stuff. I think it makes the most sense with this broad overview to combine the diffie-q and the linear and talk about them at the same time. When we reviewed for both exam 1 and exam 2, I first talked about the diffie-q and then I talked about the linear separately. But they're getting tied enough together that I think it'd be useful and beneficial to talk about them at the same time here. So since the last exam, as a quick overview of what we've done with diffie-q, very quick, we were starting to talk about linear systems in exam 2, but we got into more depth with them with regard to knowing what a solution is, how to verify something's a solution, numerical approximations with Euler's method, existence and uniqueness. We haven't had time for that kind of thing in class, but it was in the lectures. Specific models in the lectures like free fall, including with air resistance. And then starting to solve linear systems, observing that there are sometimes straight line solutions that motivates eigenvalues and eigenvectors. And then we have this method for finding solutions with eigenvalues and eigenvectors and drawing phase planes. I will talk about the linear systems, but let's focus on possibly nonlinear systems first. So we got our general nonlinear first order vector differential equation. ODE means ordinary differential equation. d vector y dt is equal to some vector field. In general, we call that capital F. And in general, the vector field could depend on both time and y. That's a possibility. This is equivalent to some sort of system of scalar equations. And in the two-dimensional case, we would typically let vector y have components little x and little y. And the first equation would be dx dt equals something, and the second equation would be dy dt equals something. What would those somethings be? You could call them little f of t comma x comma y and little g of t comma x comma y. You should understand the idea of such a system, the idea of how it would, the solutions would be graphed in some phase plane. Solutions are parametric curves that travel around the phase plane as t increases. In theory, they could do something wild. Maybe you're here when t is 0, so that's your initial condition vector. Capital Y sub 0 is what that is, capital Y sub 0. And maybe at t equals 1, you're right here, say. And the arrow indicates the direction of motion of the curve as t increases. Parametric curves are something you learn about in Calculus 1, maybe a little in Calc 2 and multivariable calculus. Some of you might be in that at the same time here. That's your position vector. For any given value of y, you're at a certain point y of t that you could think of as being a point or a position vector. Either way is okay. And then it's following the vector field. At that moment in time, the vector field would be tangent to the curve. The curve would be tangent to the vector field. And so the arrow for the vector field would have a certain direction and a certain length. And its length would be the speed of the curve. This would be the velocity vector for y of t at this moment in time. You could call it dy dt. And it equals the output of the vector field at that moment in time. Pretend T is something specific when you think about that. So that's the conceptual framework for thinking about solutions of vector equations in a phase plane. When the vector field is non-autonomous, it's time dependent. That means the arrows in the vector field can actually change over time, and that actually means solutions can cross themselves or cross each other. However, in the autonomous case, the vector field does not depend on time. It's just an f of y. The arrows in the vector field do not change over time. And existence and uniqueness theorem says distinct solution curves can't cross. They can't touch each other. A solution curve can't even cross itself with a non-zero angle. It could come back to where it starts, forming what's called a periodic solution. When I talk about the van der Pol equation in the lectures, that's an example of a periodic solution. It could come back to where it starts with the same tangent vector, but it can't cross itself with some sort of different tangent vector, different velocity vector for autonomous systems. You should know that's a consequence of uniqueness. So that's some general theory you should understand the concepts of. And then we also have Euler's method, which I haven't emphasized here in our class, but is in the lectures and in the book, and you had homework on it, so you should be able to do it. And in general, you should be able to handle Euler's method, even if it's non-autonomous. The next value of t, call it Tn, is the previous value of t, Tn minus 1 plus delta t, your step size. And the next value of y, call it yn, is the previous value of y, call it yn minus 1 plus the change in y, which is approximated by taking the value of the vector field at Tn minus 1 comma Yn minus 1 and scaling it by delta t. Better to probably put the delta t in front here. That's a scalar times a vector, making the whole thing a vector. It's not a dot product. That's an approximation to the change in y along a solution curve. And it's a good approximation if delta t is small. How small is small? It depends on the nature of the vector field. We don't get real precise there. Generally speaking, smaller values of delta t lead to better approximations of solutions, though there's a price to pay, there's more steps to do. I like thinking about Euler's method in vector form, though the textbook thinks about it in terms of the scalar functions, little f and little g. Either way is okay. I just like thinking about it in vector form. It's both convenient and conceptually easier to understand, actually, if you think about it. Okay, I don't have the time to explain it right now. Okay, so that's some pure differential equations. Now let's get into the differential equations with linear algebra stuff. And there's kind of two tracks that we're going along since the last exam. There's one track with the vector spaces and the basis of a vector space, dimension of a vector space, kernel of a linear transformation, that kind of stuff. And another track we're going along is computing eigenvalues, eigenvectors, making use of those things. They are related. Let me still go ahead and label this diffie-q with linear. One track over here is vector spaces. Another track over here is eigenvalues and eigenvectors. Vector spaces are an abstract idea. In the lectures, I do emphasize the abstract nature. What is a vector space? It's just a set that's got an addition defined on it called vector addition, and for which you can multiply by scalars, scalars typically being real numbers for us. You can even create a more general theory where the scalars could be complex numbers or even just rational numbers, but we don't want to go there. For us, we're satisfied with real number scalars. You got vectors and scalars that satisfy properties that have names: commutative property, associative property, distributive property. There's a zero vector. V plus 0 is V, no matter what V is. If you multiply any vector by the scalar 1, you get that vector back. 1 times V is V. Are some of the examples of the abstract properties. And when you think about a vector space, you're typically thinking ordinary vectors, right? Column vectors, 2-dimensional, 3-dimensional, maybe even 4-dimensional. But the theory applies to other things, including what I call function spaces. Function spaces are vector spaces. Every function space is a vector space, where the vectors, quote unquote, are functions. The individual points in the vector space, the function space, are functions. If t squared is in the vector space, t squared is a point in that vector space. Conceptually, it's an object. It's one single object. We use the word point for short, a shorthand. Should we draw them as literal dots? Well, you could, though that's not what people usually do. If you do, it does turn out to be useful, we'll see before exam 4, to sometimes think that way. It's a useful conceptualization. Is it literal? Well, it depends on what you mean by the word literal. You got linear transformations. You've got the ordinary ones that are defined by matrices. But now we've got new kinds of linear transformations. This even showed up a little bit on exam 2. Like T of F is F double prime plus 4F prime plus 29. I picked 4 and 29 on purpose there to relate it to the example from earlier. That's called a second order linear differential operator. Fancy name for something that takes a twice differentiable function, f, finds its second derivative, adds 4 times its first derivative, and then adds 29. I guess I should do times the function. I could plug in a particular function, like, oh, e to the 2t. Little t is a variable representing time in the usual sense. Capital T is the function name of this linear transformation. What do I have to do? I have to find the second derivative. If I do, I'll get 4e to the 2t. I just differentiated in my head there twice. If I do 4 times the first derivative is 2e to the 2t. Multiply by 4, I get an 8e to the 2t. And then 29 times the function. What is this simplified to? I guess 41e to the 2t. What happened there? I didn't get 0. Well, it's because this function is not in the kernel of this linear transformation. It's not a solution of the corresponding differential equation, where this is 0 on the right side. It'd be a homogeneous differential equation. I'm using f's here. I could use y. I could do t of y equals y double prime plus 4y prime plus 29y. It'd be the same thing. This is the output of this linear transformation when the input is e to the 2t. It's not 0, so this is not in the kernel. What is the kernel of this? It would be the solution set of this scalar differential equation. Can that be figured out from what we did before? It actually can be, from what we did 20 minutes ago or so. If all I care about is a solution for little y, not vector y, but scalar little y, for the second order equation, I didn't care about the vector equations, I could still find the solution from what I did. Just take the first components and form a linear combination of those. The kernel of t here is the set of all functions of the form k1 e to the negative 2t cos 5t plus k2 e to the negative 2t sine 5t, as k1 and k2 vary over all real numbers. Scalar solution set because it's a scalar differential equation. It's related to the vector one we did 20 minutes ago, but it is different. This also could be, you could say this is the span of e to the negative 2t cos 5t and e to the negative 2t sine 5t. And you could also say these two functions are linearly independent. They're not scalar multiples of each other. And the solution space is a two-dimensional vector space. Therefore, this is a basis. Not only does it span, but it's also a basis. That's a fuller justification of calling this the general solution. You know, when we write down a general solution, we don't typically write it as a kernel. I'm just doing it here just to relate it to these ideas from vector space theory. Other things we did with vector spaces included more things with matrices, finding basis for the null space of a matrix, for the column space of a matrix, technically also for the null space of its transpose, and the column space of its transpose, which is the same as the row space of the original matrix. You should know the algorithms for finding bases for those things, relate them to the Rank-Nullity theorem. Those topics were kind of some pure linear algebra whose applications to differential equations not so clear. You could argue it's got applications to differential equations in terms of giving you other conditions for when your matrix A is invertible. And that could possibly help you solve the differential equation. But on the surface, it doesn't seem to have much to do with differential equations. Again, the other track is the eigenvalues and eigenvectors. Defined by this equation, A minus lambda, A times V equals lambda times V. Realize here when you look at this equation, A does not equal lambda. This does not imply A equals lambda. A is a matrix, lambda is a scalar. A is the output of the vector field. If the vector field happens to be linear, you could call it f of v, or maybe t of v if you preferred. Lambda v is a scalar multiple of v. It's a take v and stretch it or shrink it, make it go in the opposite direction. You're wondering, are there any non-zero vectors v where the output of the vector field is parallel to the position vector of the point? Such vectors are called eigenvectors, and the corresponding value of lambda is called eigenvalue. And like I mentioned last time, this equivalent to the equation A minus lambda I times V equaling 0. We're looking for non-zero solutions for V. Therefore, we look for the values of lambda that make this a non-invertible matrix. So the kernel is non-trivial. Null space is non-trivial. So we set the determinant of this equal to 0, and we find that in a 2x2 case, you get a quadratic with two roots, two eigenvalues. If A were a 3x3 matrix, This would be a determinant of a 3x3 matrix, more complicated formula for the determinant, but you'd still set it equal to 0 and solve for lambda to find the eigenvalues, but you'd have a cubic equation instead of a quadratic. You would not be able to use the quadratic formula. You would have to be lucky to be able to factor it. Hopefully, Dr. Kinney would give you an equation that's factorable. Right? Yeah, I would. Maybe even just by guessing. Graph the characteristic polynomial, and you can see from the graph what its roots look like. Hopefully, they're nice numbers. But the overall procedure for then finding the general solution, in the case where you have real eigenvalues, is that in general, you write down an arbitrary linear combination of particular solutions. I'm writing n of them here, though mostly we've done the case where n is 2. Assuming you get linearly independent solutions, which will be the case if the eigenvectors you find are linearly independent. Then these y's will be linearly independent solutions. Which will also be the case when your eigenvalues are distinct real numbers. And that's almost always the examples we consider. We do consider some other examples after exam 3. But so for our examples, the lambdas end up being distinct real numbers or distinct complex numbers, complex conjugates. The eigenvalues being distinct real numbers does turn out to imply that the corresponding eigenvectors are linearly independent. And if there's n of them and your solution space is n-dimensional, then they'll form a basis, and this will be a general solution, which you can use to solve initial value problems. You don't want to forget about relating this to the phase plane. When is the origin a sink, a source, or a saddle point? It's a sink if both real eigenvalues are negative. It's a source if both real eigenvalues are positive. And it's a saddle point if when you have real eigenvalues, one is negative and one is positive. In the complex number case, complex eigenvalues, for our example, we got a sink, a spiral sink. There are no straight line solutions there. You're going to get a sink when the real part of the eigenvalues is negative, -2, and you'll get a source when the real part is positive. What about the real part 0? It's called the center. Yeah, you get periodic solutions that go around the origin and come back to where they start when the real part is 0, when the eigenvalues are purely imaginary numbers. To wrap all this up, we should talk about the matrix exponential and flows. First of all, there's this thing that I call the beautiful generalization. That a generic initial value problem, linear, has unique solution y equals, I'll go ahead and use phi notation. I'll use this phi for the solution function. And this equals the matrix exponential of TA, e to the TA, times the column vector y0. That's the initial condition vector. That's what I call the beautiful generalization, that this is the unique solution. I think it's also worth mentioning the main theme with general difference equations. Yn is a times yn minus 1, where it's understood that the initial condition is still y sub 0. The unique solution is yn equals a to the n power times y0. Take the matrix a to the n power and multiply times the initial condition vector. You can write that kind of thing down without thinking about matrix exponentials, without thinking about flows. But now to relate these two things, well, there's the matrix exponential. We also want to think about flows. The flow idea helps relate these two ideas. For the flow, what I mean when I say the word flow is I'm talking about what I also call the time t maps. Use a curvy phi, superscript t of y0. It's the exact same formula as the solution. You still use the matrix exponential, e to the ta times y0, the exact same formula. You just think about it differently. Here we think of y0 is fixed and t is the variable, giving us a parametric curve in the plane for the two-dimensional case, in three-dimensional space for the three-dimensional case, in n-dimensional space for the n-dimensional case, a curve moving around as t increases. Here, if you think of t as fixed and y0 as the variable, you get what's really a linear transformation. The matrix e to the ta times the vector y0, that's a linear transformation. Phi superscript t is a linear transformation from Rn to Rn in general. It's a linear transformation when t is fixed. What's simplest is to let t equal 1, the time 1 map. You just replace t with 1 and you get e to the a times y0. And the difference equation that you get when you use the matrix exponential as your matrix, like this, has solution ultimately equal to e to the na times y0, which matches the solution of the differential equation when you replace t with n. You might say big deal, but it's really useful. And the lectures I talk about the eigenvalues and eigenvectors of e to the a and how they're relevant. I came up on a homework problem too. They're related to each other. The eigenvalues of e to the a are related to the eigenvalues of a. Same with the eigenvectors. Whether the origin is a sink or a source or a saddle with the differential equations depends on the sign of the real part of the eigenvalues. Whether it's a sink or a source or a saddle for this one depends on whether those eigenvalues are bigger than 1 in magnitude or less than 1 in magnitude. And when I talk about the magnitude of an eigenvalue in a general complex number eigenvalue, I'm talking about how far it is from the origin in what's called the complex plane. That's a 10-second introduction to a kind of difficult idea. But they do come out in the lectures there. We're doing this in part to relate these two ideas, to relate differential equations and linear algebra. We're also doing it in part for when we get to chapter 5, because it allows us to do some things we wouldn't be able to do otherwise. A lot of pretty advanced ideas. Let me know if you have questions. Have a good day.